A star torn apart by a black hole can outshine an entire galaxy. By watching until the end, you will discover exactly how this cosmic catastrophe unfolds, what it reveals about hidden black holes, and why these rare events are rewriting our understanding of the universe. How can such a brief, violent encounter teach us so much about the invisible monsters lurking at the centers of galaxies? And what happens to the stars remains long after the flare fades. Do you think we will ever catch one of these events happening in real time? That moment of destruction begins at a very specific point in space, a boundary known to astronomers as the tidal force limit. For black holes, this works the same way as the more familiar Roche limit that can tear apart moons near a planet, but the forces involved are far more extreme. When a star wanders too close to a black hole, the difference in gravitational pull across its body becomes overwhelming. The side of the star facing the black hole feels a much stronger pull than the side facing away. This difference, called a tidal force, stretches the star until the star's own gravity can no longer hold it together. The critical distance where this happens depends on the black hole's mass. A more massive black hole has a larger event horizon, but its tidal forces are actually gentler at a given distance because the gravity gradient is shallower. So a supermassive black hole, millions of times the mass of our Sun, will pull a star apart from farther away, but the stretching process unfolds more slowly. A smaller stellar mass black hole creates sharper tidal forces that shred the star much closer in, and the process is more violent and quick. Either way, once the star crosses that invisible line, its fate is sealed. The star cannot remain a sphere. It becomes distorted, first into an egg shape, then into a long, thin stream of gas. This process has a vivid name: spaghettification. It is not a metaphor. The star really does stretch into a strand of plasma, like a noodle being pulled from both ends. The material from the star does not all fall into the black hole at once. Some of it swings around and forms a hot, swirling accretion disk. The rest continues on a looping orbit, eventually spiraling inward. So the moment of disruption is not the end of the story. It is the beginning of a brilliant, temporary flare that can outshine all the stars in the galaxy combined. And it is at this exact moment that astronomers begin to watch, because the way the star is torn apart reveals secrets about the black hole that would otherwise remain hidden. As the star swings around the black hole on its final approach, its spherical shape starts to warp in a way that is both gradual and devastating. The side closest to the black hole feels the strongest gravitational pull, while the far side lags behind. This uneven tug stretches the star into what astronomers describe as a cigar shape, long and narrow, with its middle bulging slightly from the compression of gases being forced together. The transformation does not happen over millions of years. It unfolds in just hours or days, a blink of cosmic time, making it one of the fastest large-scale events in the universe. During this rapid distortion, the star's surface begins to tear. Streams of hot plasma peel away from the outer layers, spiraling inward like water being sucked down a drain. But before the star is fully shredded, something else begins: intense heating. As the star is squeezed and stretched, friction within its gases generates enormous temperatures. The material near the black hole can reach millions of degrees, glowing so brightly that the flare becomes visible across billions of light years. It is a moment of extreme pressure and energy, a preview of the cataclysm to come. And yet, the star itself is still mostly intact, clinging to its identity even as it is pulled apart from the inside out. What happens in the next few hours will decide how much of the star's mass escapes forever and how much gets consumed, setting the stage for the brilliant fireworks that follow. And then, in a single catastrophic instant, the star's structure fails completely. The immense tidal forces overcome the star's own gravity, and what was once a cohesive ball of plasma shatters into a long, chaotic stream of stellar debris. This is no clean break. It is a violent, tangled flood of superheated gas, heavy elements forged in the star's core, and swirling plasma, all ripped apart and sent flying in different directions. The star is gone, replaced by a glowing river of matter that stretches for millions of miles. In that moment, the black hole does not simply swallow everything. It takes only the portion that gets caught in its gravitational grip. Roughly half of the shredded material is flung outward on hyperbolic orbits, escaping the black hole entirely and shooting into deep space at tremendous speeds. The other half remains gravitationally bound, trapped in a tight, chaotic orbit that will slowly pull it inward. This two-part division is crucial. The escaping debris creates a faint but expanding cloud of gas and dust, while the bound material begins its long, spiraling journey toward the event horizon. It is this bound material that powers the brilliant flare astronomers observe, a beacon that lasts for months or even years, so the moment of disruption is not the end. It is the spark that lights the cosmic firework, a release of energy so intense that it rewrites the star's legacy from a quiet life of fusion into a final, spectacular announcement of its own destruction. That bound debris does not fall straight into the black hole. Instead, the shredded stellar material begins its journey on wildly eccentric orbits, like comets looping around the sun but far more extreme. These streams of superheated gas swing out to great distances before swooping back in close to the black hole, crossing paths with other streams of debris. And this is where the real action begins. When those fast-moving streams collide, they crash together with tremendous force. The collisions rob the gas of its orbital energy, causing it to settle into a more circular path. Within weeks or months, the chaotic cloud of debris organizes itself into a flat, rotating structure spinning around the black hole, a temporary accretion disk. This disk is not like the stable, long-lived disks found at the centers of quiet galaxies. It is a violent, short-lived whirlpool, a structure that forms rapidly, evolves quickly, and will eventually fade away. The gas in the disk does not simply sit there. It spirals inward because of friction, but this is not ordinary friction. As the gas rubs against itself, it heats up to extreme temperatures through a process called viscous heating. Imagine stirring a thick soup so fast that the spoon heats up from the resistance, but on a scale where the soup is million-degree plasma and the spoon is gravity itself. That heat transforms gravitational potential energy into intense radiation, X-rays, ultraviolet light, and visible glow that can be seen across the universe. The disk glows brightest in its inner regions where the gas is densest and moving fastest. There, near the black hole, temperatures can reach tens of millions of degrees. This is what astronomers detect as a tidal disruption event. A flare that rises sharply, peaks, and then slowly fades over months or years as the disk drains away. Unlike the steady hum of a galactic center powered by gas flowing in continuously, this disk is a one-time feast. Once the star's matter is consumed, the disk vanishes and the black hole returns to silence. But while it lasts, it becomes one of the most luminous objects in the observable universe. A brief window into the feeding habits of a cosmic giant. And it is during this intense, fleeting phase that the black hole's hidden properties are written across the light we receive. The accretion disk becomes a cosmic lighthouse, visible across billions of light years. This is the flare. It erupts suddenly, releasing a torrent of radiation across the entire electromagnetic spectrum, from high-energy X-rays down through ultraviolet and visible light, and sometimes even into radio waves. The signal does not rise gradually. It spikes sharply, often within days of the star's disruption, and then fades over months as the disk slowly drains onto the black hole. Astronomers detect these flares using space-based telescopes like the Swift satellite and ground-based surveys that scan the skies every night. When they spot a sudden brightening at the center of a quiet galaxy, they know something rare is happening. One of the best-studied examples is a flare designated ASASSN-14li, discovered by the All-Sky Automated Survey for Supernova. At its peak, this single event shone with the light of roughly 20 billion suns, rivaling the entire galaxy that hosted it. And that galaxy was not even active. It was a quiet, ordinary collection of stars until the flare turned its core into a cosmic beacon. The light we observed came not from the star itself, but from the superheated gas swirling just outside the black hole. As the material spiraled inward, it reached temperatures of millions of degrees, glowing brightest in X-rays. But the flare also produced strong ultraviolet and optical emissions, allowing telescopes around the world to track its evolution across multiple wavelengths. Interestingly, some tidal disruption events also generate radio emission, which can appear weeks or months later. This happens when fast-moving outflows or narrow jets of plasma plow into surrounding gas, producing a secondary glow that lingers long after the main flare fades. The event Swift J1644+57 was one of the first to show this kind of jet, a focused beam of energy that briefly made the black hole appear even more luminous. For astronomers, this flare is everything. It is the primary signal. Without it, we would never know that a black hole had just torn apart a star. And because the flare carries information about the black hole's mass, its spin, and the nature of the star that was destroyed, each new detection adds another piece to the puzzle of how these invisible giants feed and grow. The flare does not last, but while it shines, it tells a story that spans cosmic distances. Spotting these cosmic fireworks demands a global network of robotic telescopes. Astronomers cannot predict when a star will wander too close to a black hole, so they must keep watch over huge swaths of sky every single night. That is where all-sky transient surveys come in. These automated observatories scan the heavens repeatedly, comparing new images to previous ones. When a pixel suddenly brightens, an alert goes out. One of the most productive systems today is the Zwicky Transient Facility, or ZTF, based at Palomar Observatory in California. Every clear night, ZTF captures hundreds of images covering thousands of square degrees of sky. Its rapid cadence means it can spot a new flare within hours of its appearance. Since it began operations, ZTF has discovered dozens of tidal disruption events, turning what was once a rare curiosity into a regularly studied phenomenon. But an even more powerful survey is on the horizon. The Vera C. Rubin Observatory, currently under construction in Chile, will carry out the legacy survey of space and time. Once operational, Rubin will image the entire visible sky every few nights with a massive 3.2 billion pixel camera. It is expected to find hundreds of tidal disruption events per year, a true flood of data. When a candidate flare is flagged, astronomers then examine its light curve, the graph of brightness over time. A tidal disruption event has a very distinct shape, a rapid rise to peak brightness over days to weeks, followed by a slow, steady decline that follows a specific mathematical pattern. This power law decay is a signature of the accretion disk draining away. Supernova also brighten and fade, but their light curves often show more irregular features or a longer plateau. Active galactic nuclei, the steady glow from supermassive black holes that are always feeding, do not flare and fade in the same way. Spectral signatures provide another crucial clue. When astronomers split the incoming light into its component wavelengths, they see broad emission lines from hydrogen and helium. These lines are broad because the gas is moving at tremendous speeds, thousands of kilometers per second, as it orbits near the black hole. If the spectrum shows only narrow lines or lines from different elements, the source is likely something else. Still, even after an all-sky survey flags a candidate, confirmation requires follow-up observations with space-based telescopes. The Chandra X-ray Observatory, XMM-Newton, and the Neil Gehrels Swift Observatory can detect the high-energy X-ray emission that is often the true mark of a black hole feeding event. Swift, with its rapid response capability, can turn to a new target within hours. When a tidal disruption event is confirmed across multiple wavelengths, the data becomes a goldmine for understanding not only the star that died, but the hidden black hole that killed it. Each new detection brings us closer to answering the biggest question of all: how many of these events are happening, and what do they tell us about the black holes that lurk in almost every galaxy? Not all black holes tear stars apart in the same way. The mass of the black hole itself decides whether the star even has a chance to put on a show. For the smallest black holes, those born from the collapse of a single star with masses roughly 10 to 100 times that of our Sun, the encounter is often too fast and too violent to produce a visible flare. The star approaches, crosses the tidal force limit, and is either swallowed whole or shredded so close to the event horizon that the debris falls in almost immediately. There is no time for a glowing accretion disk to form, no brilliant spike of light. The star simply vanishes, and the black hole grows by a tiny fraction, leaving behind no signal for astronomers to detect. These events are likely common throughout the universe, but they remain invisible to our telescopes. On the other end of the scale, a supermassive black hole with a mass greater than about 100 million suns presents a different problem. Its event horizon is enormous, stretching across a region larger than our entire solar system. When a star approaches such a giant, the difference in gravitational pull across the star is too gentle to tear it apart. Instead, the star remains intact all the way to the event horizon, where it crosses directly into the black hole. This is called direct capture. The star is consumed whole, and again, no flare erupts. The black hole swallows its meal without a trace. So where does that leave us with visible tidal disruption events? They happen in a sweet spot between these extremes. The black hole must be massive enough to have a strong gravitational pull, but not so massive that it destroys the star before it can be shredded, and not so small that the material falls in too quickly. Astronomers estimate that the ideal range for observable TDs is roughly 100,000 to 100 million solar masses. Within this window, the tidal forces are just right to stretch and tear the star into a glowing stream, allowing a temporary accretion disk to form and shine for months. It is a delicate balance. The black holes that produce these cosmic flares are not the largest or the smallest. They are the ones sitting in a narrow middle zone, and that makes them some of the most informative objects in the universe. Each flare we catch tells us not just about the star that died, but about a black hole that is just the right size to reveal its secrets. Why are there so few black holes in this range? And what does their rarity say about how galaxies evolve? The answers are hidden in the light of these dying stars. But not every close encounter ends in complete destruction. Some stars survive barely, after losing only their outer layers to the black hole's gravitational grip. In this scenario, the star does not cross the tidal force limit entirely. Instead, it grazes the boundary, and the black hole peels away its outer envelope like a cosmic hand stripping the skin from an orange. The star's dense core remains intact, still held together by its own gravity, but it emerges from the encounter scarred and violently heated. Its surface temperature skyrockets as the removed material exposes hotter interior layers. The star becomes a strange, bloated remnant, glowing with a fierce, blue-white light that fades slowly as it settles back into equilibrium. What makes these partial disruptions so fascinating is that the star often does not escape to safety. Its orbit may be highly eccentric, meaning it swings out far into the galaxy, and then comes screaming back toward the black hole on a looping path that takes months or years to complete. Each time it returns, it loses another thin layer of material. The process repeats like a cosmic clock ticking away with each periastron passage, the closest point in the orbit. Astronomers have long theorized that such recurring partial disruptions could produce a distinctive signal, a series of bright, periodic flares that rise and fade at regular intervals. Observational evidence for these events has been mounting in recent years. A handful of galaxies have been found to emit powerful X-ray bursts that repeat every few hours or days, a phenomenon astronomers now call quasi-periodic eruptions. The leading explanation for these eruptions is a low-mass star or even a white dwarf orbiting a supermassive black hole on a very close, eccentric orbit. Each time the star swings in, the black hole strips away a small amount of material, which falls inward and generates a brief, intense flash of X-rays. The star survives, battered and shrinking, but it keeps coming back. The eruptions are not perfectly regular because the star's orbit can change slightly after each encounter, but the pattern is unmistakable. Just a few years ago, this was purely theoretical. Now, facilities like the European Space Agency's XMM-Newton telescope and NASA Chandra Observatory have identified several candidate sources that fit the profile almost perfectly. These quasi-periodic eruptions offer a new window into the immediate vicinity of supermassive black holes. They tell us that the feeding process is not always a single, dramatic meal. Sometimes it is a series of small bites taken from the same star over and over again. The star itself becomes a messenger, its shrinking size and changing orbit revealing the black hole's mass and the geometry of space-time around it. And because these events repeat, astronomers can plan observations in advance, catching each eruption with multiple telescopes to build a detailed picture. The star might endure hundreds or even thousands of these close passes before it finally loses too much mass and is torn apart completely. Until then, it continues its deadly dance, a cosmic survivor that keeps brushing against destruction and pulling away, each time leaving behind a tiny piece of itself. Could our own galaxy's central black hole be hosting such a star right now, waiting for us to spot its next flare? Half of that shredded star does not fall inward. It is flung outward at speeds reaching 10,000 kilometers per second. This is not a gentle breeze. It is a violent, high-velocity wind of superheated gas and heavy elements, blasted away from the black hole with enough force to travel across the entire solar system in just a few hours. As this material tears away from the accretion disk, it carves a path through the sparse gas and dust that fills the space between stars in the galaxy. That collision generates powerful shock fronts, like sonic booms but on a cosmic scale. The shocks heat the surrounding medium to millions of degrees, causing it to glow brightly in radio wavelengths. This radio afterglow often appears weeks or months after the initial optical flare, lingering as a faint, expanding shell that astronomers can map over time. The outflow does not just produce a beautiful glow, it also changes the environment around the black hole. Some of the ejected gas, especially the lighter elements, can escape the galaxy entirely, carrying away mass and energy. But heavier elements forged deep inside the star during its lifetime are more likely to slow down and mix with the interstellar medium. There, they become raw material for future generations of stars and planets. In a sense, the star's final act is not just destruction, it is also a gift. Its scattered remains enrich the galaxy, seeding clouds of gas with carbon, oxygen, and iron that will one day collapse into new suns. This process is a powerful form of feedback, a way for the black hole to influence its host galaxy far beyond its immediate neighborhood. The black hole does not just consume. It also shapes the galaxy's evolution, regulating how much gas is available for star formation and controlling the distribution of elements. so that half of the star that escapes is not wasted. It becomes a sculptor of galaxies, a messenger that carries the star's legacy across thousands of light years, and a reminder that even in total destruction, there is a spark of creation. The bound material that did not escape begins its long, slow pilgrimage back toward the black hole. This falling back does not happen all at once. Instead, the shredded star's debris returns in a drawn-out trickle, following a precise mathematical rhythm that astronomers have come to recognize as a power law decay. Specifically, the rate at which material falls back onto the black hole declines as time to the negative 5/3 power. In plain language, after the initial bright flash, the amount of gas spiraling inward drops off quickly at first, then more and more gradually over months and years. This consistent pattern is a direct consequence of how the star was torn apart. The pieces on tighter orbits return sooner and get eaten faster, while the stuff on wider, looping paths takes much longer to drift back in. So the accretion disk does not drain at a steady pace. It follows a curve that starts steep and flattens out, like the tail of a firework fading into the night sky. As the fallback rate declines, the disk becomes thinner and less luminous. The intense heat that powered the X-ray and ultraviolet peak slowly drops away. At some point, the rate at which matter spirals inward falls below a critical threshold known as the Eddington limit. That limit is the maximum luminosity a black hole can produce while still pulling in gas in a stable way. Once the accretion rate sinks below that boundary, the disk transitions into a quieter, cooler state. The X-rays fade, and the light shifts toward longer wavelengths, ultraviolet and optical, where it can still be detected with sensitive telescopes. Even years after the initial disruption, this faint afterglow can linger, offering a unique window into the final stages of the meal. During this long tail, the disk's behavior becomes sensitive to details that were hidden during the bright peak. The exact shape of the fading light reveals how fast the black hole is spinning. A spinning black hole drags space-time around with it, pulling the innermost stable orbit closer and allowing gas to reach higher speeds before plunging in. This changes the efficiency of energy release, altering the decay curve in subtle but measurable ways. So by watching the star's remains fade over years, astronomers can measure the black hole's spin, one of its most fundamental properties. The disk also offers clues about the viscosity of the gas, the strength of magnetic fields, and the geometry of the accretion flow. Each of these factors leaves a fingerprint in the light curve. The star may be long gone, but its shredded debris continues to tell stories long after the initial explosion has faded from view. That faint, persistent glow is not just the end of the event. It is the quiet chapter where the most detailed science happens, a final whisper from the star that once burned bright. That final whisper carries a secret written in the language of gravity itself. As the shredded star's debris spirals closer and closer to the black hole, it enters a region where the rules of space and time begin to twist in ways our everyday experience cannot prepare us for. This is the domain of general relativity, where gravity is not just a force pulling on objects, but a distortion of the very fabric of the universe. The closer the gas gets to the event horizon, the more bizarre the effects become. The innermost stable circular orbit, or ISCO, marks the point of no return for any material trying to maintain a circular path. Inside this boundary, stable orbits are impossible. Any particle that crosses it must either plunge directly into the black hole or get flung outward on a wild escape trajectory. For the debris in the accretion disk, the ISCO acts like a final funnel, and the exact location of that funnel depends on one thing: the black hole's spin. A non-spinning black hole, known as a Schwarzschild black hole, has an ISCO at 3 times the radius of the event horizon. A spinning black hole, a Kerr black hole, drags space-time around with it, pulling the ISCO much closer in. In the most extreme case, the innermost stable orbit can shrink to just half the radius of the event horizon itself. This frame-dragging effect, first predicted by Einstein and later confirmed by experiments near Earth, becomes a powerful cosmic engine. As the black hole rotates, it literally twists the surrounding space-time, forcing any nearby material to rotate along with it. The debris does not just orbit. It is dragged around by the very structure of the universe, forced into a precessing spiral that shifts with every loop. That orbital precession means the ellipse traced by the gas does not stay fixed. Its orientation slowly rotates over time, a subtle but measurable wobble that encodes the black hole's spin rate, and there is another effect that directly bends the light we receive. Gravitational redshift. As photons climb out of the deep gravitational well near the black hole, they lose energy, stretching to longer, redder wavelengths. By the time they reach our telescopes, the light from the innermost disk has been shifted significantly toward the red end of the spectrum. The faster the black hole spins, the closer the disk can get, and the stronger the redshift becomes. So by carefully measuring the shape of the light curve and the shifting of spectral lines over the months and years of the event's decay, astronomers can disentangle these relativistic fingerprints. The exact timing of the fading, the precise color changes, and even the subtle oscillations in brightness all carry information about how fast the black hole is spinning. This is one of the few ways to measure black hole spin at all, outside of gravitational wave signals from merging pairs, and it matters because spin is a fundamental property as important as mass. It tells us how the black hole formed, whether it grew by swallowing gas steadily or by merging with other black holes, and how it has influenced the evolution of its host galaxy. So that final, faint glow from the dying star's remains is not just a fading ember. It is a gravitational laboratory, a natural experiment that lets us probe the warped space-time right at the edge of a black hole. And every new tidal disruption event we catch is another chance to turn those twisted ripples in space and time into a clear measurement of something otherwise hidden forever. Those hidden measurements are reshaping what we know about black hole populations. Consider for a moment that most galaxies in the universe, including our own Milky Way, host a supermassive black hole at their center. But the vast majority of these black holes are dormant. They are not actively feeding on gas and dust. They do not produce the brilliant, steady glow of an active galactic nucleus. They sit there, massive and quiet, completely invisible to our telescopes. We know they must exist because we can see their gravitational influence on nearby stars. But that is a slow, painstaking measurement that works only for the closest galaxies. For the billions of other galaxies scattered across the universe, their central black holes remain hidden, their presence only inferred from the structure of the galaxy itself. Tidal disruption events change this entirely. When a star wanders too close, the resulting flare does not care whether the black hole is active or dormant. It erupts just as brightly regardless. This means every TD we detect is a signal from a previously invisible black hole, a lighthouse that briefly illuminates a dark and silent core. Astronomers call these events unbiased probes, not because they catch every black hole, but because they do not require the black hole to already be feeding. Over the past decade, the growing catalog of confirmed TDs has given us the first real census of dormant supermassive black holes in ordinary galaxies. And the numbers are surprising. The observed rate, roughly 1 TD every 10,000 to 100,000 years per galaxy, sounds impossibly rare in human terms. But across the billions of galaxies we can survey, that rate adds up to dozens of events every year that are bright enough to detect. The statistics themselves carry meaning. The rate tells us something about the density of stars near galactic centers. The more stars packed into that crowded region, the more often one will stray too close. It also tells us about the black hole itself. Some galaxies produce TDs more frequently than others, and the difference seems to depend on the black hole's mass and the structure of the galactic nucleus. A galaxy with a more massive black hole might have a lower TD rate because the tidal forces are gentler and stars get swallowed whole instead of shredded. A galaxy with a smaller black hole might produce more visible events, but the flares may be fainter and harder to detect. By comparing the observed TD rate across different types of galaxies, astronomers are beginning to place statistical constraints on the mass distribution of supermassive black holes and the dynamical environment of galactic centers. This is a fundamentally new way to study black hole demographics. Before TDs, we could only measure active black holes or the few nearby ones whose gravity we could track. Now, with each new flare, we are sampling a population that was otherwise completely silent. The star that dies in that brief flash gives us not just its own story, but a window into the hidden architecture of galaxies across the universe. And as the surveys get faster and more sensitive, the sample size is growing, turning individual events into a powerful statistical picture of the invisible giants that shape our cosmos. But the numbers we are actually detecting do not match what the theory predicts. Astronomers have built detailed models of how often stars should wander too close to a supermassive black hole based on the density of stars in galactic centers and the gravitational interactions that scatter them inward. Those models suggest we should be seeing roughly 10 to 100 times more tidal disruption events than we currently observe. That gap, that huge discrepancy between what should happen and what we actually see, is one of the most intriguing puzzles in the field right now. It is not a small error. It is a chasm that hints at something fundamental we are missing about how these events unfold or how they appear to our telescopes. So where are all the missing flares? One strong possibility is that many of them are simply hidden from view by the very same gas and dust that fills the centers of galaxies. A galactic nucleus is a messy place. Thick clouds of interstellar material can absorb and scatter the bright light from a tidal disruption event before it ever reaches us. If the event happens behind a dense lane of dust, the optical and ultraviolet flash might be completely blocked. Only the most energetic X-rays might punch through, and even then, they can be absorbed if the column density is high enough. This means our current surveys, which rely heavily on visible light, are likely biased toward events that occur in relatively clean environments. The true rate could be much higher, but we are only seeing the ones that happen in clear windows of the sky. Another idea is that the rate itself is not constant over cosmic time. The models often assume a steady background of stellar interactions, but real galaxies evolve. A galaxy that recently merged with another galaxy might have a period of enhanced star scattering near its center, followed by long quiet stretches. We might be observing at a time when many galaxies are passing through a low-rate phase purely by chance. Future surveys that monitor the same galaxies for decades will be able to test this by tracking how many events occur over longer timescales. Perhaps the most fascinating explanation involves not one black hole, but two. Many large galaxies are thought to harbor binary supermassive black holes at their cores, pairs of giants locked in a slow gravitational dance after their host galaxies merge. In such a system, the two black holes can gravitationally kick nearby stars into completely different orbits. Some stars might be flung inward more often, increasing the TD rate, but others might be ejected from the galactic center entirely, reducing the number of stars available to be disrupted. The net effect could be a dramatically lower TD rate compared to a single black hole scenario. And if the binary is still in the process of hardening, its orbital energy can scatter stars so efficiently that the central region becomes depleted over time, starved of the fuel needed for future events. Astronomers studying these binary systems have found that the distribution of stellar orbits becomes chaotic, making it harder for any single star to end up on a close encounter with either black hole. Each of these explanations, dust obscuration, intrinsic rate variability, and binary black hole disruption, has its own set of predictions that future observations can test. When the Vera Rubin Observatory comes online and begins its decade-long survey, it will detect hundreds of TDs across many different types of galaxies. By comparing the observed rates in dusty versus clean galaxies, in merging versus isolated systems, and in galaxies with known binary candidates, we will start to untangle which effect dominates. And that will tell us not just why we are missing so many events, but also something deeper about the hidden architecture of galactic centers. The missing flares are not a failure of observation. They are a clue, a mystery that leads us toward a more complete understanding of the dark hearts of galaxies. Every missing event is a question waiting to be answered. Not every star meets its end alone. Some arrive at the black hole in pairs, locked together in a gravitational embrace that has lasted for millions or even billions of years. Binary star systems are common throughout the universe, and when such a pair wanders too close to a supermassive black hole, the outcome is far stranger than a single star being torn apart. The black hole's immense gravity pulls unevenly on the two stars, and the tight bond that held them together is shattered in an instant. One star may be captured into a tight orbit around the black hole, doomed to circle closer and closer until it too is disrupted in a future event. The other star, however, is flung away at tremendous speed, gaining so much energy from the encounter that it becomes a hypervelocity star, racing out of the galaxy at thousands of kilometers per second. Astronomers have observed these runaway stars in our own galactic halo, moving so fast that no ordinary gravitational interaction could have accelerated them. Their trajectories trace back toward the galactic center, pointing to a violent encounter with the Milky Way's central black hole as their origin. The captured star, meanwhile, may go on to produce its own tidal disruption event years or centuries later, a delayed echo of the binary's original destruction. This is not a single flash but a cosmic chain reaction, where one disruption can launch a star across the universe and set the stage for another flare far in the future. An even rarer and more exotic scenario unfolds when a white dwarf, the dense, Earth-sized remnant of a star like our Sun, encounters a black hole of a very particular size. Consider an intermediate mass black hole, one with a mass between a few hundred and a few 100,000 times that of our Sun. Unlike the supermassive giants at galactic centers, these middling black holes are far less common and harder to detect. But when a white dwarf falls into one, the results can be spectacular. The white dwarf is incredibly compact, held up by quantum mechanical pressure rather than ordinary heat. When tidal forces from the black hole begin to pull it apart, the compression and heating can ignite runaway nuclear fusion on its surface. The white dwarf becomes a temporary thermonuclear bomb, releasing a burst of energy that can briefly outshine entire galaxies. In some cases, the disruption can even trigger a type of gamma-ray burst, one of the most energetic explosions in the universe, but on a much shorter timescale than the long gamma-ray bursts produced by collapsing massive stars. Observational evidence for these exotic events is still emerging, but a handful of candidate flares have been detected that match the predicted signatures: extremely rapid rise times, unusual X-ray spectra, and a lack of any associated supernova. One event, known as Swift J1644+57, showed a relativistic jet that some scientists believe could have been powered by a white dwarf being torn apart by an intermediate mass black hole. Another, called at 2018 COW, displayed a remarkably smooth and fast-fading light curve that did not fit standard supernova models, leading to speculation that a white dwarf disruption might have been involved. These cases push our understanding of tidal disruption to its very limits. They remind us that the universe's dark centers are not just quiet monsters. They can turn the dense remnants of dead stars into cosmic fireworks, and they can launch entire suns across the void, forever changing the landscape of the galaxy. And with each new detection, we ask ourselves, how many more of these rare and violent meetings are happening right now, beyond the reach of our telescopes, waiting for us to look in the right place at the right time? A new generation of telescopes is about to rewrite everything we know. The Vera Rubin Observatory in Chile, with its gigantic 3.2 billion pixel camera, will soon begin scanning the entire visible sky every few nights. That is 100 times faster than any previous survey. When it starts operations in the next few years, it is expected to discover not tens but hundreds of tidal disruption events each year. Suddenly, these cosmic catastrophes will go from rare, headline-grabbing finds to routine astronomical occurrences. Astronomers will be able to build real statistical samples. Instead of studying one event in detail and guessing, they will compare dozens of events side by side, separating the typical from the bizarre. They will finally measure the true rate of stellar disruptions across different types of galaxies and test whether the missing flares we talked about earlier are hidden by dust or simply rarer than models predict. With hundreds of events, rare subtypes will emerge from the noise. Partial disruptions where a star survives multiple close passes may become a distinct class. White dwarf disruptions by intermediate mass black holes could be identified by their unique, rapid light curves. Even binary star disruptions and the resulting hypervelocity stars might be traced back to a specific flare. But the revolution is not only on the ground. New space-based missions are designed to catch the earliest moments of a tidal disruption, when the star first begins to tear and the fresh debris glows hottest. Ultrasat, an ultraviolet survey satellite led by Israel and NASA, will detect the initial flash of UV light within hours before the event even peaks in visible wavelengths. The Einstein probe, a Chinese-led mission with European collaboration, will scan the sky in soft X-rays, capturing the very first emission from the innermost, hottest gas swirling just above the black hole. Together, these telescopes will give us a view of tidal disruption events from the very first second, showing the star's initial shredding and the formation of the accretion disk in real time. It will be like watching the explosion of a firework from the spark instead of just the bright burst. The data will be rich enough to measure black holes spin directly from the early light curve, revealing the hidden angular momentum of dormant giants across the universe. We are standing at the threshold of a golden age for tidal disruption research. Every night, more than a dozen new telescopes will watch the sky, waiting for that one pixel to brighten where nothing shone before. And when it happens, the story of a star's last moments will no longer be a single case study. It will be a chapter in a vast, growing encyclopedia of cosmic violence and rebirth, written in the language of light and gravity. The next few years will not just answer old questions, they will open doors we did not even know existed. From that first fatal drift toward the black hole to the fading glow of its scattered remains, every step of this cosmic drama carries meaning. The star began its journey as a quiet, stable sun, burning hydrogen in its core for billions of years, until a random gravitational nudge sent it on a collision course with an invisible giant. It crossed the tidal force limit, stretched into a strand of hot plasma, and shattered into a river of debris. Half of that material was flung outward to enrich the galaxy, while the other half spiraled inward to form a temporary accretion disk glowing with the light of 20 billion suns. That flare traveled across space for millions or billions of years, carrying the star's final message to our telescopes, and even after the peak faded, the long, slow decay of its remains revealed the black hole's spin, the nature of space-time near its edge, and the hidden architecture of the galactic center. This journey from birth to disruption to luminous end is not just a spectacle. It is a natural experiment, a way to illuminate the hidden lives of supermassive black holes that would otherwise remain completely silent. It tests our theories of gravity and accretion, showing us how matter behaves under the most extreme conditions in the universe. It helps explain how galaxies and their central monsters co-evolve, how the growth of black holes shapes the formation of stars and the distribution of elements across cosmic time. And with each new event, we get closer to answering the fundamental questions. How common are these encounters? What determines whether a star gets shredded or swallowed whole? And what do these rare flashes tell us about the invisible giants at the hearts of nearly every galaxy? The story of one star's end is a thread in a much larger tapestry, connecting the smallest particles of gas to the largest structures in the cosmos. If you have made it this far, you already understand why these cosmic catastrophes matter. Now help others discover them too. Like this video to tell the algorithm that this kind of deep, thoughtful science content deserves to be seen. Subscribe so you do not miss the next journey into the unknown. And in the comments, share your own question about black holes, tidal disruption, or anything else that keeps you looking up at the night sky. The universe is full of stories waiting to be told. Thank you for watching.